Today, we want to go back to looking at double integrals. And this time we're going to introduce a new set of coordinates called polar coordinates. We want to accomplish the same thing. Let's go back to our base problem. The integral over r of f of xy dA will give us the volume under the surface f of xy and above the region r in the xy plane. We do this by taking the function as the height multiplied by the area, which is either a dx dy or a dy dx. And we do this for all the points in R. So the integral is saying plug in all these points into this expression, f of xy dA. That'll give you a little piece of the volume, add up all those. What we want to change up is how we describe the points in the plane. We want to change how we're describing the point. Rectangular coordinates is just one way to describe all the points in a plane. We have a horizontal coordinate and a vertical coordinate. So here's the point 4, 3. It's above 4 on the x-axis and next to 3 on the y-axis. But that's not the only way that we can describe this location. The other way we can describe this location is with polar coordinates. For polar coordinates, we want to know how far that point is from the origin and what angle from the positive x-axis. So those are going to be our two coordinates. A distance from the origin and an angle measured from the positive x-axis. In this case, clockwise or anti-clockwise is going to be positive. So we could also describe this point as r theta in polar coordinates. This is just another way of describing locations in space. We usually start with rectangular coordinates, because that's what we're familiar with. We set up our cities and towns and little grids. And so we can identify your location with a horizontal and a vertical, a street and a number. We could also have set up the town by describing the angle that you take to get to your house and how far your house is from the center of the town. That would be describing, making an address with polar coordinates. So instead of horizontal and vertical, we have angle and distance. Any questions? We've seen polar coordinates before. These are the same polar coordinates. We just want to remind ourselves. Let's suppose that we have rectangular coordinates 4, 3, and we want to find the polar coordinates. What we can do is pull out this right triangle and see that r is the hypotenuse, and I've got a triangle with a base of 4 and a height of 3. So we have 3 squared. 4 squared plus 3 squared is equal to r squared. So that 0.43 is 5 units from the origin. The values that we know are opposite. The y is opposite and the x is adjacent. So we could use tangent of opposite over adjacent. If we have things going the other way, if we have polar coordinates and we want to convert to rectangular coordinates, we can note that the y is opposite theta and x is adjacent to theta. And so we can say x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. We can think of writing sine of theta is opposite y over hypotenuse r. So if we solve that for y is r sine theta. Any questions? Now let's look at the pieces that we need to take this polar coordinate stuff and add it to our double integral. The important piece that we're going for, the thing that we want to look at is what's the dA in polar coordinates. In polar coordinates, what's the dA supposed to look like? Excuse me. Let's first think about what dA represents in rectangular coordinates. So the dA that we're using is some small change in x multiplied by some small change in y, making some small area. We have some small change in x. Multiplied by some small change in y. So the dx and the dy are a length and a width, and dA is just length times width for the area of that small rectangle. So we're thinking of the dx as, say, a width, and the dy is a length, and so dA is an area. So the dA is a small piece of area. That's why we get the dx dy or the dy dx. We're doing length times width. So presumably we need to do the same thing when we're dealing with polar coordinates. The dA needs to represent an area. Excuse me. But in polar coordinates, instead of being on a grid, in polar coordinates, only one of the coordinates represents distance. So the dr is some small change in radius. That is a length. So the grid looks a little bit different. It's very close to being a rectangle, depending on how small we make the angle theta. But the change in theta, the d theta part, that's an angle. I can't use d theta, some small change in angle, and multiply it by a length to come up with an area. It doesn't make sense to take 5 inches and multiply by 30 degrees. You don't get an area. 30 degrees is a measure of angle, not a measure of length. So we need to turn this change in angle to a change in length. So d theta is a change in angle. Not in length. So the expression dr d theta doesn't mean anything. dr is a length. But d theta on its own is not a length. It's a change in angle, not a change in length. So what we do is we look at these curved parts. First of all, we imagine that this little curved piece is a rectangle. If we keep dr small enough and we keep d theta small enough, then it looks like a rectangle. So for small dr and d theta, that little bit is close to being a rectangle. This is for small changes in r and d theta. So what we're going to do is use the dr as the length, and we're going to take the width as the arc length. We're going to try to find this distance. We're going to treat the arc length as the width. dr is the length, and then the arc length is going to be the width. Then all we have to do is remember our formula for arc length, which is just the radius multiplied by the change in angle. The change in angle represents some fraction of an entire circle. And then we just have to multiply by the radius. If we go around an entire circle, that's 2 pi radians. And the circumference around that circle will be 2 pi times the radius. Arc length is that same calculation. We just call it circumference when we find the entire circle, but that's just a special case of arc length. Arc length is the radius multiplied by the angle. So the arc length, which we want to use as the width of our close to being a rectangle, is r times d theta. So dA in polar coordinates we use r times d theta times dr. We need that factor of r attached to the d theta to turn d theta into a length. We need that factor of r to turn the d theta into a length. All right. Let's take a look at an example. And let's start with an example with which we are familiar. So we're going to think about a double integral where r is the circle of radius 5. This is one that we know in in rectangular coordinates. So let's make sure that this fits first. This circle is a circle of radius 5. So we can describe it as x squared plus y squared is equal to 25. So if I want to make a double integral for this region, if I want to get the whole circle, I can make a dy dx integral or a dx dy integral. In this case, x will go from negative r up to r, and y will go from negative r to r as well, because I'm asking for the entire circle. I forgot to switch to printing press mode. Oops. Then I started writing down incorrect stuff, and I made a rectangle. I don't normally edit my videos, so you're going to have to pretend that this part has been edited out. So we've written this integral before. If the y's go from negative r to r, those are the constants, and the x's will go from the square root of 25 minus y squared up to the positive 25 square root of 25 minus y squared. Or we can write it in the other direction. So we know how to write this integral when we're dealing with rectangular coordinates. Now we want to describe this region in polar coordinates. Now let's describe the region in polar coordinates. Since we're going all the way around, our theta is going to go from 0 all the way around to pi. So theta will go from 0 to 2 pi. And the radius is going to start at the origin, and we want all the circles up to a radius of 5. So the radius will start off at 0 and stop at 5. Notice that everything here is constants, the radius, because we're just dealing with a bunch of circles. And polar coordinates are really good at circles. So our double integral in polar coordinates, first of all, we'd have to convert our function to a function of r and theta. But for dA, I can't just write d theta dr because d theta is not a length, it's a change of angle. So we have to have r d theta dr. R d theta is a length, dr is a width, so r d theta dr is an area. Oh, we're also going to have, we can't just trade our r's for x's and our thetas for y's. We'll have to convert the function to polar coordinates. Now, written this way, the d theta is the inside integral and dr is the outside integral. The r's go from 0 to 5, and the thetas go from 0 to 2 pi. We could switch the order of integration, go from dr d theta instead of d theta dr. And we should always be able to do that. So let's write the double integral. Function isn't going to change, but we're going to have to make sure it's in polar coordinates. We still need r d theta to be the width, and then dr can be the length. But in this case, r is the first integral. That'll go from 0 to 5. And the last integral will go from 0 to 2 pi. So d theta dr, the outer integral is the r, inner integral is the theta. And dr d theta, it's the other way around. Any questions? One thing that should happen is that if we integrate this function, if we integrate the function 1 over r dA, then we should get the area of the region. So integrating the function 1 should give us the area. We know that the integral of 1 dA will give us the area of the region. So let's see if that's true. Notice that I'm replacing the function with one. That r is part of the dA. So this r is part of the dA. So the integral of r with respect to theta is r times theta, evaluated from 0 to 2 pi, dr still. R is constant with respect to theta, so I just integrate d theta and come up with r theta. Now we plug in from 0 to 2 pi on theta. So we want to integrate from 0 to 5, 2 pi r dr. Plug in 2 pi, plug in 0 and subtract, we'll get 2 pi r. Now we integrate with respect to r. So we get pi r squared, evaluated from 0 to 5. And we get 25 pi, just as we suspected. Just as what we knew what was supposed to happen. The other integral will do the same thing. It's not going to make much difference since we're plugging in just constants. But if we integrate r dr first, then that'll give us the pi r squared. We integrate with respect to theta. And that'll give us 25. That'll give us I forgot what the function was already. I should just write it down clearly. I'm having difficulty. So in this case, integrating r with respect to r will give us a half r squared, evaluated from 0 to 5. So we'll integrate from 0 to 2 pi, 25 over 2. Now we just need to integrate with respect to theta. The integral of 25 over 2 is 25 over 2 theta. And we evaluate from 0 to 2 pi. And we still get 25 pi, the area that we knew we would get. This is why we pick things like circles to do for example, because we know what the area is supposed to be, and so we can check it against what we know, check that our integral works and gives us the value that we know we're supposed to get. Any questions? Was everybody there? So all we have to do now is practice working with polar coordinates so that we can describe regions to integrals. Instead of saying what's x between and what's y between, we're going to say what's r between and what's theta go between. So for example, if I just wanted this first quadrant, if I just wanted this quarter circle in the first quadrant, r goes from 0 to 5, and theta will go from 0 to pi over 2. If I wanted to cut out a slice, let's say in the second and third quadrants, but I only want a half of a ring, I could have theta go from pi over 2 to 3 pi over 2. And if if I want to subtract a circle of radius 3, I could integrate r equals 3 to r equals 5. So that would control how much of the hole in the middle, the size of the hole in the middle, and theta tells us how far we go around. Any questions? Slide along. All right, so that's what we want to do. moving forward, we want to start thinking not just in terms of rectangular coordinates, but also in terms of polar coordinates. On this example, I could use this to say that polar coordinates are better at some things than, at this point, we should point out that polar coordinates are going to be better at some functions and worse at others. Notice that rectangular coordinates, if I have this region here, which is like this half of a washer, rectangular coordinates are going to be kind of bad at that. Because I've got two circles. I got a top circle and a bottom circle. But then the top circle and the bottom circle stop, and it's just the top circle and the bottom of the bottom circle. And plus I've got this extra piece down here. And if I slice it horizontally, I'm between this circle and the y-axis until I get to this point, when it's this circle, big circle and little circle, until I get to the top of little circle, then it's big circle and y-axis again. Three separate integrals that I'd have to integrate over for this weird half of a washer on string. But in polar coordinates, it's very simple. We just integrate r from 3 to 5, and we integrate theta from pi over 2 to 3 pi over 2. Because that is pretty much a rectangle in polar coordinates. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.